Hi students, welcome back to the session on free vibration. So in the previous video, you have seen the types of damping and equation for a free damped vibration. And we have seen the three conditions, that is over damped, under damped and critically damped conditions. So now we're going to see the analysis of those three. So analysis of over damped system. So where eta is greater than 1. So when I want to substitute this equation, so in this solution, so I want to get the roots. The roots are real as well as distinct. So I'm going to get, so given by s1 is equals to minus zeta plus root of eta square minus 1 multiplied by omega n, and s2 will be equals to minus zeta minus root of zeta square minus 1 into omega n. Then the solution of the differential equation becomes x equals to c1 e to the power of minus zeta plus root of zeta square minus 1 multiplied by omega n into t plus c2 e to the power of minus zeta minus root of zeta square minus 1 omega n into t. So this is the final solution for a overdamped system. The constants C1 and C2 can be identified by determining the initial conditions. So the typical response curve of a damped system is shown in the next slide. So the amplitude increases exponentially with time and becomes 0 at t equals to infinity. So the major thing to find C1 and C2 is by taking the condition as x equals to 0 and t equals to 0, and second one will be x dot is equals to v naught and t is equals to 0. So this condition I want to substitute the values. I want to get the overall equation of the system, which says that whether those conditions to identify the value of displacement. So when you go for the response curve, you can see that the motion has been started over here. It takes for the amplitude. Once the amplitude reaches, so since it is over damped, it comes to a 0 at time t equals to infinity, but it won't complete a complete motion, so you don't get a sine wave over here. So you don't get any periodic motion in the over damped system. So coming to the next condition, the analysis of a critically damped system. So that is the major thing. So when you go for a critical damped system, that is eta equals to 1. So in this case, the roots will be equal. So that is S1 will be equals to S2 is equals to minus omega n. So when you go for minus omega n, so the solution of differential equation becomes x1 c1 x equals to c1 e to the power of s1 into t plus c2 t into e to the power of s2 into t. So I'm going to substitute the values minus omega n I'm going to substitute. So I'm going to get equation as x equals to c1 plus c2 t multiplied by e to the power of minus omega n into t. So x is equal to x naught. Conditions t equals to 0 are x dot equals to v naught and t equals to 0. So this is the final solution for a critical damped system, and constant C1 and C2 are obtained by applying these conditions. So the typical response curve is shown in the next slide. So in this case, the amplitude decreases at a faster rate and compared to the overdamped system. So overdamped and critically damped systems, you won't produce a periodic motion completely. So whereas overdamped, it takes a lot of time to come to 0, whereas critical damp, with a shorter time, it comes to a 0. The best example for a critical damp is your gun with a trigger. When you're going to trigger the gun, what will happen? It's going to start to vibrate, but you don't complete the motion. It automatically come to halt at a fraction of seconds. So you can see in the graph, this is the graph you can see where it equals to 1, 2, 5 and 10. So when it is 1 critically damping, it comes to 0 with the lesser time compared to the overdamped system. Coming to the third one, the major one, so which is required for a design engineers to design a vibrating system, is underdamped system when you are going for a damping. So in this case, the roots are very complex, conjugate, and are given by this. Since it is less than 1, I'm going to get a imaginary values over the roots. So it will be in terms of cos theta and sin theta. So when I want to go for that, S1 is equals to minus theta plus j root of 1 minus theta square minus 1. Since it is minus, what will happen is when you're going to substitute the values in this equation, it will be minus 1 square minus 1. So when I'm going to go for that values, so again I'm going to get a minus value over here. So it will be very difficult to get the minus. So I'm going to take the j outside. So the solutions will be like this. So I'm going to take j over here. So the solution of differentiation becomes x equals to c1 e to the power of minus eta plus j root of 1 minus eta square into omega n into t plus c2 e to the power of minus eta minus j root of 1 minus eta square into omega n into t. So this equations can be written as x is equals to e to the power of minus eta omega n t are going to take as common. So I'm going to write this equation. So now the relation e to the power of I theta can be written as cos theta plus I sin theta. So e to the power of minus I theta can be written as cos theta minus I sin theta. So equation will be rewritten as x e to the power of minus eta omega n into t. So I want to write the complete expansion over there. That I want to take the common c1 and c2. So I want to get x e to the power of minus eta omega n into t multiplied by c1 plus c2 multiplied by cos root of 1 minus eta square into omega n into t plus j c1 minus c2 multiplied by sine root of 1 minus eta square omega n into t. So the equation, so c1 and c2 plus j into c1 minus c2 are real quantities. So and hence the equation can be written as, so x is equals to e to the power of minus eta omega n into t multiplied by a into cos root of 1 minus eta square omega n into t plus b sine root of 1 minus eta square omega n into t. So I am going to write the overall equation. So it is simple as a1 e to the power of minus eta omega n into t multiplied by sine root of 1 minus eta square omega n into t plus pi 1. So pi is nothing but the phase angle and a will be your amplitude. So now in this case I want to replace root of 1 minus eta square omega n with the term as omega d. So omega d is nothing but natural frequency under damping condition, which is called as damped natural frequency of the system. So I want to replace that with this equation, that is x is equals to a1 e to the power of minus eta omega n into t multiplied by sine omega d into t plus pi 1, where a1 and pi 1 are determined by applying the initial conditions. So the typical response curve under damped system is shown over here. This is the thing you can see here. As the time progresses, the amplitude of the vibrating system is completely reducing. So this reduction is also called as logarithmic decrement, that we'll see in the next video. So the time period is given by 1 or 2 pi divided by root of 1 minus eta square into omega n, and a and b are the two amplitudes, and this indicates the time, that is exponentially it going to reduce. So applying the initial condition, that is x equals x naught, t equals to 0 and x dot equals 0 and t equals 0, then finding the constant a1 and pi 1. So equation becomes x equals to x naught divided by root of 1 minus eta square multiplied by e to the power of minus eta omega n into t multiplied this. So this again you can replace with the terms as omega d. So this term is nothing but the amplitude of the vibration which is observed to decay exponentially with the time. So when you go for this three condition, that is underdamped, overdamped and critical damped, the underdamped system is the one which is preferred for the maximum systems, where just we're going to control the vibration from going to the extreme. Overdamped, it won't provide the motion, so automatically it's going to affect the body, where they don't go for a to and fro motions, automatically go for a failure. Critically damped, it is needed only where it is has to be so vibration has to be restricted for a fraction. So the next video you're going to see about the logarithmic decrement.